print one of these? Okay. We'll look together. Get you move your back here. Okay, so this is like our final. This is, like I said, the final exam I gave last spring. But anyway, the first set was matching, and I list some different kinds of problems that we've done, and then we're going to read different, just short scenarios and decide what kind of problem it is. So, just to kind of briefly go back over these, the one sample t-test, you have one sample, and you're looking at averages or means. It's a quantitative variable. The matched pairs, it's really the one sample t-test, but it's for when you have before and after or pre-test, post-test. So you'll subtract and then get the x's that way and then do that. I'm going to skip down. The other quantitative problems will be the analysis of variance, which is option G on here. So you're talking about difference between means again, but there's more than two groups. So on the exam, probably three groups. And then the other quantitative variable problem is the linear regression, where you have two different quantitative variables, and you're trying to see if there's a linear relationship between the two. Then the other three tests that are on here, the one sample proportion, the two sample proportion, and the chi-square test, are all things that deal with a qualitative variable. So if you're just talking about a binomial variable and you just have one sample, it's one proportion z-test. If you have two samples, two sample proportion z-test, and the chi-square is just a cross-classification where one of the variables, one of the qualitative variables, or at least one, is multinomial. So on this first one, it says the average time it takes to drive from Russellville to Dallas over 5 hours. You're asking about average. You have a quantitative variable, which is time, and there's just one sample. So we're just asking, when we ask, just how long does it take to drive there? And if you make it in 5 hours, you're probably driving over the speed limit. But I've made it in 5 hours. So anyway, average quantitative variable, one sample, that is a one sample t-test. You guys can ask questions at any time if you would like. Okay, so the next one on there is the average time it takes to complete a stat exam less than 3 minutes. Okay, so I messed up on the 3 minutes. I have had people finish in 3 minutes, but it was because they didn't know anything and they just threw the test down and left. But you probably wouldn't pass it in 3 minutes. But anyway, it is asking about average. Again, it's time, a quantitative variable. And there's just one sample. So again, that is a one sample t-test. Okay, and the next one is there a linear relationship. That's all you need. So the next one says, is the percentage, so a percentage is the same thing as a proportion. So we're dealing with the problem of proportions. So is the proportion or the percentage of restaurants with a vegetarian option higher in Arkansas than it is in Louisiana? So since there's two states that we're looking at, two groups, and it's percentage or proportions, that one's going to be the two sample proportion z-test. Qualitative variable, when we go to a restaurant, the question we're asking of the restaurant would just then be our element. The question we're asking about the restaurant is simply, do you have a vegetarian option or not? Okay, the next one, we've got averages. So we're talking about either one sample t-test, matched pairs, two sample t-test, or ANOVA, since we're talking about averages. But it says higher in northwest Arkansas than the average for Little Rock, two groups. So average, two groups, two sample t-test. Okay, got another one with average. So again, if it's average, we know we're talking about one of those, average quantitative variable. time it takes to receive the order. But it's different for these fast food restaurants. And so whoever's doing this is going to 4 different restaurants. And so since that's more than 2 groups, that's ANOVA. Okay, the next one asks relationship. Now for me that's enough. Notice it doesn't say linear relationship. So it's probably going to be the chi-square test. But you can look here and you can say one variable is where they live, what's the region, and there are 1, 2, 3, 4, 5, 6 regions. So that's just a qualitative variable, what region, and then whether or not they have a recycling program. Again, that's just whether or not they have that, a binomial variable. So basically, you know, you were setting this up. It'd be a 2 by 6. You just count the number in each one of those 2 qualitative variables. Chi-square test. And then does the time it take, well, after, before. Matched pairs. Make sure on the matched pairs, I noticed I've been looking at some of the retake exams, and I'm getting quite a bit of hypotheses, research hypotheses say mu A greater than mu B. But there's only one sample. That means there's going to be one mean. So in the matched pairs, your HR, since it's time, improvement will be, if you've selected the second post minus the pre, would be mu less than 0. So it's always just going to be one mean, and it's going to be compared to 0, either not equal to, greater than, or whatever. And that whether it's less than or greater than will depend on which way you subtract. Average, 3 groups. Have over 40% bought a lottery trick in the last week. There's just one sample, and it's asking about a percentage, which is the same thing as a proportion. So that's going to be one sample proportion. And this is just one of the match the correlations to the graph thing. So we've got 0.79 minus 5.5 minus 7.7 and minus 9.8. So the 0.79 is pretty easy. It's the one it's the only one that's going rising. The others are all downward slope. So that one's pretty easy. Probably the next easiest one is minus 9.8. You know, you're going to see that everything's real close to the close together there. So we're now just down to the minus 5.5 and the minus 7.7, and this one on the top right. Those are a little bit closer together. I think noticeably closer together than these are, more scattered. So that's going to be the minus 0.55. Okay, this is where you might want to have your calculator out. And this one, we have 100 students are selected to read this novel, and they read the novel. And of those that read the novel, 78 passed the test. So, you know, the ones that read, we had N of 100, and X, the number that passed. This is a qualitative variable. They either passed or they didn't. We're not getting average scores or anything. And so the p-hat for that group is 0.78. And in the second group, instead of reading the book, they just read the Spark Notes. Imagine someone doing that. And then took the exam. And out of those 100, this is group B, that just the Spark Notes. Out of those 100, 67 passed for a proportion of 0.67. So anyway, that's just reading the problem. The first part here says if the sample size is large enough to support statistical inference. Remember, this is a qualitative variable. So we're looking to see whether the number of yeses and nos are greater than 5. This one tends to, on the sample size problem, because we did the quantitative with the 15, 40, 100, this one tends to give a little more problem for folks. So in the first group, 78 said yes. That's out of 100, so 100 minus 78, or 22, said no. And in the second group, 67 said yes. And since there were 100 total, 100 minus 67 is 33. And so what you're looking at is, are all of these yeses and nos greater than 5? And so they're all greater than 5. So the sample size is large enough. So we're going to get the 98% confidence interval on this one, and we're looking at the difference between two population proportions. We had two qualitative variables. So on your calculator, if you would just hit stat, test, and then I think it's 2 proportion z, and make sure you get the one with interval. And then you just have to enter in, I think, 78, 100, 67, 100, and 98 for the confidence interval. And I think if you do that, you will get something like minus 0.0358. That's the lower bound of the confidence interval. And then carrying this all the way out, I got 25578. The key thing, so that's the interval, that's the answer to that part. And the next part, based on that interval, can we conclude there's a difference? And the answer to that is no. And that's because this interval goes across 0. Okay. So the interval includes 0. And of course, if the difference between any two numbers is 0, they might not be different. I'm moving too fast for you guys. Okay, so then the next part, of course, I'm going to ask about interpreting confidence intervals. And in this case, our statistic is the difference between the two sample proportions. So whatever your statistic is, that's what goes on the axis. And then in the center is the true, we don't know what it is, but the true value of the parameter. In this case, the parameter is the difference between the two population proportions. And so it has some true value. So if we just kept on sampling, theoretically, all possible pairs of samples of 100 from each one, and then just kept on constructing confidence intervals, then we're going to have a distribution of those intervals, or a collection of intervals. So of that collection of intervals, %98 will include the true, we don't know what it is, but the true PA minus PB. So somewhere in the interval, it doesn't have to be any specific place in the interval, So 98% are going to be like that. But we know up front, when you do statistics, there's always a chance of error. We've constrained that in this case to, in the long run, a 2% chance of error. So 2% will not include the real difference. So we know coming in when we construct the intervals that 2% of the time our interval is not going to include the real parameter. It's a trade-off. You'd like to always include it, but then your interval would be so wide it didn't make sense. It's like the example I gave earlier in the class with estimating grade point, saying it's 2 plus or minus 2. That doesn't do you any good in terms of estimation, so you have to give up some certainty in order to get a meaningful interval. Okay, so the next one, we had a random sample of 100 Walmart customers, 58 who use the checkout. So they either do or don't use the checkout. It's a qualitative variable where we have 58 people who answer yes, if you want to think of it that way, out of a total of 100. Of course, that would make the sample proportion equal to 0.58. And then it says, is this enough evidence to conclude that over half answer yes, that they use the checkout? So half is 50% or 0.5. So HR is P, the population proportion, greater than 0.5, and the null hypothesis is always no effect. In this case, P is equal to 0.5. So this one we're going to use the p-value, and we're going to draw the sampling distribution. I didn't check here, but the number of yeses are 58, the number of no's are 42, so we know this is going to be a bell curve. And on the axis, you just put what's a symbol for the statistic, and in the center, basically HO. P is equal to 0.5. Then we have the statistic that we computed from the data, and you're just going to locate it on this sampling distribution. And the p-value is just the area in this tail. And you can use your calculator for this. So it's just going to be stat test, and you're going to go to the one proportion z-test. It's maybe the, I don't know, fifth or sixth thing down on there. And in the, where it says HO, the first thing there anyway, you put 0.5. And then your X and N are going to be 58 and 100. When you get down to the hypothesis, you'll put greater than, whatever symbol there is in the research hypothesis. And I got that to be 0.0548. And the next part said test the hypothesis using the p-value. And it says, should you reject if the level of significance is 0.05? So we're going to reject HO if the p-value is less than 0.05, less than whatever you set for the alpha. And our p-value that we found was, I should write that out all the way, p-value is equal to 0.0548, which is not less than 0.05. So we don't reject HO. Just circle the no there. I'm going to go back one slide to answer this next question. I'm going to make that if-then statement, and it'll be, I think, a little easier to see if we're back on this slide. we're basically just putting into words the sampling distribution. So if P is equal to 0.5, if HO is true, then there is a 0.0548 chance, whatever the p-value is, of getting a p-hat. Our p-hat was 0.58, but we're going to say, and that we're going greater than that. So a p-hat, a sample statistic, greater than 0.58. And you can put greater than or equal to if you want. It doesn't make any difference in a continuous distribution. That's something that historically some people miss, more so than some of the other questions. That's that confidence interval thing too. So, you might want to asterisk that. Another thing is that matched pairs. That's why I wrote that hypothesis up there. It tends to be one of the things that people are going to miss. Okay, so this next one is the thing we just did, I guess, last Tuesday on forecasting. So we have 6 weeks of data, and then with 6 weeks, and then sales for each week. We're going to develop 2 kinds of forecasts, one using time series regression and one using the 3-month moving average. Then we're going to use the model, which would have been best, the least amount of error had we been using it in the past. I think I have these numbers on the next slide too, so we'll have a little more room. So for the time series regression, we're going to get the forecast for week 7. And so we're going to have an equation which is sales is equal to A plus B times the time. It's in that general form of any linear equation, A plus BX, where A is the y-intercept and B is the slope. So you just put these in your calculator. Put, this is X, put it in whatever list you want to. And this is Y, put that in whatever list you want to put that in. Okay, and so when you do that, then go stat, tests, Lin regression t-test. It's a little easier to get to. It's closer if you arrow up instead of down. And so you do Lin regression t-test, and then just tell it to put what list you put the X in and what list you put the Y in. And then I know you have to put not equal to on the hypothesis. And just tell it what list you're in. I think that's about it. I'll check again.
Did you put it not equal?
Yeah, we're only going to run as a two-tailed test. It really can be either. But in here, we're just going to run it as a two-tail always, so just not equal to. And then hit calculate. Well, actually, in this one, it doesn't make any difference, so we're not going to test a hypothesis. But when we get to the regression problem, we'll just do all those as two-tailed tests. Okay, I think actually I might have taken this data out already. But anyway, you should get 7.2 plus 1.23 times X, which is which week you're in. And we're forecasting for the 7th week. So we're just going to put 7 into that. 7.2 plus 1.23 times 7. And that's equal to, I got 15.81. And so that's the forecast using the time series regression. So we also want to forecast using that moving average, which you'll sometimes just see. That's just moving average. You'll see it abbreviated like that. But anyway, we're doing this for a 3-week moving average. So to get this forecast for the 7th week, just take the average of the last 3 weeks. So week 4 was 14, week 5 was 12, and week 6 was 15. And there's 3 of them. So our forecast is 13.67. And if this were in like thousands or 100,000s of units, that's a pretty big difference. And you're going to build all of your budget off of your sales forecast, so we want to know which one of those would be the best to use. So what we'll do is we'll use each one of those as if we had done it before. And so we can't do the moving average until week 4. So this is my moving average column. And so in week 4, we're going to have 8 plus 11 plus 9 divided by 3. Always the previous 3 weeks. And then for the next week, 11 plus 9 plus 14. That should be divided by 3 right there. And then for week 6, we'll have 9 plus 14 plus 12. Again, divided by 3. And I got those to be 9.33, 11.33, and 11.67. And then what I'm going to do is I'm going to see how much those would have been off had I been using them in the past. So in week 4, I'd predict 9.33, but I actually got 14. So I'm off by 4.67. And that's just 14 minus 933. You make sure you don't need any negative numbers here. Just take the absolute value. And then in the next week, off by 0.67, and in week 6, off by 3.33. And so for this model, the MAD, the mean absolute deviation, is going to equal 4.67 plus 0.67 plus 3.33. All of that divided by 3, and that's 2.89. So that's just the average amount you would have been off in your forecast had you been using them to forecast in weeks 4, 5, and 6, using the data that was available at each of those times. So I'm a little short on space here. To get the time series regression forecasts, you're going to take this sales equation here, and for the week, you're going to just put in 4, 5, and 6 into the equation. And if you do that, in week 4, you would get 12.12. Again, that's just 7.2 plus 1.23 times 4. And then 13.35 and 14.58. And then I'm going to get, again, the difference between each of those and the numbers we actually ended up getting. So the ADs here are 1.88, 1.35, and 0.42. So this last one, for example, is 15 minus 14.58. And then the MAD for the time series regression is equal to 1.88 plus 1.35 plus 0.42, all of that divided by 3, and that's 1.22. So you want to be off by as little as possible, and the 1.22 is less than the 2.89. So that means you should use the time series regression forecast. So the forecast that you should use is this 15.81. It would have been better had we been using it in the past. Okay, on the next one, this is just the written part of the problem, and I'm not going to read it all. You can read it on your own, but I am going to point out that it says pre-test and post-test, and that's just like before and after. So you know this is going to be the matched pairs t-test, and the data's on the next problem, or next page. The first question is, are the sample sizes large enough to support statistical inference in this problem, and explain? Well, the sample size is 16, so whether it's large enough or not depends on whether or not it has outliers or extreme values. If it's a normal population, you know it's fine. If they're skew, you know it's fine because we're more than 15. So as long as there aren't outliers or extreme values, the sample size is large enough. Now what you could do is draw a box plot. I'm probably not going to ask you to do that on this problem, but we'll see. For now, we're not. We're just going to say as long as there aren't outliers or extreme values. Anyway, are sales higher after the promotion than before? HR, matched pairs, one mean greater than 0. HO, one mean equal to 0. So to do this on the calculator, you'll need to put the pre-test and post-test values in your calculator. And then let's say, for example, that you put these pre-tests in list 1 and the post-tests in list 2. Then what you want to do is go to the heading in L3 and highlight the L3 at the top of the list, and then just type, it's going to put it down at the bottom here, type L2, your after score, minus L1, and hit enter, and that's going to fill in a column in L3, and it's going to have numbers like 8 minus 7, it's going to have 1, 3, 0, 2, and so on. And so the stuff in list 1 and list 2 really becomes irrelevant for the test now. It's the stuff that's going to be in, this is L3, that we're going to do the test on. And it's one sample, and it just really is those differences that's X. Well, anyway, once you have that in there and you have the L3, you're going to hit stat, test, t-test, and then the hypothesis value that you put in there is 0. You make sure, I should have said this first, that when you do the stat, test, t-test, that at the top it gives you a choice between stats and data. And this one we're going to use the data that's stored in list 3. We're not just going to put in means and standard deviations. So make sure you've highlighted data. Then you'll put 0 in the hypothesis at the top. You'll tell it your data are in list 3. You'll select greater than, the same sign that's in HR, when you get down to that. And then just go down and hit calculate. Okay, it says use the critical value approach. So we're going to have to look up a critical value in the t-table, and then compare what we get on the calculator. So the degrees of freedom in this problem is n minus 1, or 16 minus 1 is 15. And we have a one-tailed test because it's just greater than. And alpha was 0.5. So if you look that up in your t-table, you're going to get 1.753. So we're going to reject HO. if t-test is greater than 1.753. And when you did all that stuff in your calculator, you're going to come up with a t-test which is equal to 3.72. That is greater than 1.753. So you're going to reject HO. And you're going to conclude that there was improvement, which is mu greater than 0. Remember on this test last year, this one gave people a little bit of a problem. And I'll tell you, this particular thing says Bonferroni up here. I'll be using 2 key intervals, but it's going to be just like this. The numbers might be slightly different. But anyway, it's saying here that you've already done a one-way ANOVA, and you've concluded there's a difference on sales for at least one difference between means for strategy of price, convenience, and quality. So now you're doing the test after that, like the HSD test, and you want to know which specific means are different and what strategy you ought to recommend. So you look over on the right-hand side at the confidence intervals, and the first one we're going to look at is price and convenience. That interval goes from -18 to almost 4. That interval includes 0. So you should have no preference between price and convenience. For the next one, price and quality, it's about 43 to 65. And we read this in the same direction that we have it on the chart here. We're saying that price leads to somewhere between 43 and 65 more units of sales than does quality. So we should prefer price. We should prefer a price strategy rather than one based on quality. I know you're used to everybody telling you, well, we've got to be concerned with quality and everything. But if you're selling cheap crap, then price is more important than quality. So on the next one anyway, we've already done convenience and price. This is just going to be, the numbers are going to be reversed over here. So the next one we need to do is convenience and quality. And convenience is somewhere between 50 and 72 greater than quality. So you should also prefer a convenience rather than a quality approach. So again, price and convenience we couldn't tell a significant difference between those, so we're going to use one of those. Basically, the conclusion of this one is, for this product, don't use a strategy based on quality. People don't care about it for this product. Okay, the next one is, do we have enough evidence to conclude there's a relationship? That should already clue you in, even if I didn't have the chart here, that we're doing a chi-square problem. But it's between where a person grew up, over here. We're just putting things into categories. So there's 4 categories. That's multinomial. And their use of alcohol. We're just we're not measuring means here. We're just putting them into categories: never, occasional, and more than occasionally. So these numbers in the center of the table are just frequencies in each cross classification. So it's a chi-square test, and I think I have another slide where okay, here we go. Write the research and null hypotheses, and the HR is that there is a relationship between the region where someone grew up and the alcohol consumption, or which category of alcohol consumption someone was in. And HO is that they're not a relationship or that they're unrelated. Then we're going to use the critical value approach. We're going to reject HO if chi-square test is greater than some value, always a one-tailed upper. And let me go back to the last one. To get the degrees of freedom, you could, if you wanted, just blot out one row and one column, and so there's 6 cells left. That's the degrees of freedom. Or you could just do degrees of freedom is the number of rows minus 1, number of columns minus 1, and we have 4 rows minus 1, so that's going to be 3, times 3 columns minus 1, that's 2, and 3 times 2 is 6. So we've got 6 degrees of freedom. So I'm going to reject HO if chi-square test is greater than, and on the chi-square table, if you go to alpha 05, I know I didn't put the alpha, yeah, I guess I did, it's up at the top there. Alpha 05 and 6 degrees of freedom. That's going to be 12.59. I don't have that table with me. Got all the rest of them. It's got just that's it. Just a very few numbers on it. So just get in the column 05 and go down to 6 degrees of freedom. Okay, this says use your calculator for the calculation. So this one works a little bit differently than the other ones. What you do is you set up a matrix and put the values in there. So since you go to the matrix, it's second, and it's about the 3rd or 4th button down on your left-hand side. Yeah, the 4th one. So just hit second and matrix, then arrow over to edit and hit enter. And then tell it that you have a 4 by 3 matrix at the top, 4 by 3, 4 rows by 3 columns. And then just when you have that matrix there, just put in the numbers that are on the table, 21, 45, 80, and so on. And then do stat test, then arrow up to the chi-square test. Depending on which calculator, they might have 2 chi-square tests on there. One of them says GOF. It's the other one, the one that doesn't have the, it's a goodness of fit test, which is just another test. And then hit enter, and then if you left things alone, then we put the numbers in A, so just leave that the same. B, just leave that the same. Just go down and hit calculate. So once you've gotten the numbers in the matrix, this part's pretty easy. And then you should see on your output that the chi-square test is equal to 11.35, which is not greater than 12.59. So you fail to reject HO, and you conclude that there may not be a relationship. Between where someone grew up and their use of alcohol. A lot of writing on this one. Anyway, there's three kinds of toothpaste. You can see that on the output. And we're looking for a difference between means. So this is going to be an analysis of variance. Note that I gave you the mean and the variance for the first two groups. And so you're going to have to compute the mean and the variance of the third group and then proceed with the analysis of variance. So let's see. I think the first thing I want to do is just write down the means for group A. That was, I'll try to organize this a little better. The mean was for A was 25, and the variance was 15.2. The mean for group B was equal to 33, and the variance for group B was equal to 12.8. So for group C, we're going to add up the numbers here, and that's 84. So x bar C is equal to the sum of the x's divided by n, or 84 divided by 6, which is, I believe, 14. And then we're going to get the deviations. So 17 minus 13, 17 minus 14 is 3. I'll just fill these in now. Then we're going to square those deviations. And add all of that up, and I got 50. And so then the variance for group C, be careful on this one, don't take the square root. It's just the sum of the x sub I minus x bar squared divided by n minus 1. So we had 50 divided by 5 is equal to 10. Why this is a little fresh here, before I write the hypothesis and stuff, I'm going to go ahead and make some calculations. I'm going to get the mean of the means. That's just going to equal x bar A plus x bar B plus x bar C divided by k, the number of groups. So 25 plus 33 plus 14 divided by 3 is, I think I got 24. And then the mean square treatment is equal to NA x bar A minus x bar bar squared. And just do the same thing for the next two groups. And all that's divided by k minus 1. Again, k is just the number of groups that we had here. And so we had 6 per group. 25 minus 24 squared plus 6, 33 minus 24 squared plus 6, 14 minus 24 squared, and all of that divided by 3 minus 1. And that's equal to 546. Then MSE is just equal to the average of the 3 variances. And we've already squared these, so don't do any squaring again. So our first variance was 15.2 plus 12.8 plus 10 divided by 3. And that comes out to be 12.67. So, I'm going to go back now and do the hypotheses and all of that. So, HR is at least one of the following is true. Mu A not equal to mu B. Mu A not equal to mu B. I'm sorry, C. Mu B not equal to mu C. Make sure you get the at least one, because it's not all of them or just one of them, it's at least one. And HO is that all three population means are the same, or that they could be the same. So we're going to reject HO if the F test is greater than some values, like the chi-square, always one tail upper. So we'll need some degrees of freedom for this. I'm going to put those over here. The degrees of freedom for the numerator is equal to k minus 1. 3 minus 1 is 2. And the degrees of freedom for the denominator is the total sample size minus k, which is 18 minus 3 is 15. So you go to your F table, make sure you get the F and not the Q, and you'll get 3.7. The F test is equal to MSTR, the mean square treatment, the difference between the three means, divided by error. That's the variances. 546 divided by 12.67. I got 43.1. That is greater than 3.7. So we reject HO and conclude that at least one of these is true. Then, which specific pairs of means differ? You can do these two steps in whichever order makes the best sense to you. I'm going to get the difference between each set of sample means. So A and B, that's the absolute value of 25 minus 33, that's 8. And then for A and C, 25 minus 14, that's an absolute value difference of 11. And then $33 minus 14, and that is 19. So those are just the differences between the respective pairs of means. Then I'm going to compute a cutoff, the Tukey's HSD test. That's equal to Q times the square root of MSE divided by the group sample size, or the sample size of any one group. That's, of course, the same as NA or NB or NC. And the Tukey's test assumes that you have the same exact sample size in every group. There are other tests to use if that's conditions not met. Okay, the degrees of freedom for Q, for the numerator, it's just equal to K, which is 3. And for the denominator, it's the same thing it was for the F test. So for 3 and 15, look that up in your Q table. You'll get 3.67. And then the MSE, we had that earlier to be 12.67, and the size of each group was 6. And that comes out to be 5.33. So all of these are greater than 5.33. So that means that there are differences between all pairs of corresponding means. So for mu A, we can see that this one's less than that one. It's reasonable to conclude that mu A is less than mu B. And in the next one, mu A is greater than mu C. And in the next one, that mu B is greater than mu C. You could have said this one, mu B greater than mu A. That might help you get them in order a little bit. So the smallest one, C. The biggest one is B. So if more is better, go for B, then A, then C. You could summarize that like this. Mu B greater than mu A greater than mu C. That just summarizes the stuff that you have there, and it's a little bit easier to interpret once you have it. Yeah. Okay, the next problem asks if there's a linear relationship between hours of training and worker productivity. So I'll have to work this one out as we go through here. I was working it this morning, and then some other students came by from another class wanting to get some help with statistics. They had a test today. So I guess you probably can't wait till you get to operations management so you can have some more of this. Well, anyway. If you add these up, you get 102. And so x bar, I'm going to put this over here, is equal to the sum of the x's divided by n, which is 102 divided by 6, and that's 17. I'm going to go ahead and get the standard deviation for those. Subtract 17 from all of these. And then square those. You get 190 for that. So Sx is equal to, and this time, standard deviation, so you do take the square root. Six numbers there, so n minus 1. And I got 6.16. Then when I add it up for the y's, I got 306. So y bar is equal to the sum of the y's divided by n. 306 divided by 6, that's 51. Minus 1, minus 11, minus 11, 19, 17, and minus 13. And then square all of those. Then add. It's 1062. So the standard deviation of the y's got 14.57. Okay, then we need to get the covariance of x and y. So that's going to be the sum of the cross products, no squaring here, divided by n minus 1. So for the cross products, I'm taking the x deviations and the y deviations, circling them so I can keep it straight there. I got 0, minus 99, 4, 64. Wait. Sorry about that. That's why I usually do the cross products before I get the... okay, minus 2 times 11 is 22. Minus 8 times 19 is minus 152. 5 times 17 is 85, and minus 4 times 13 is going to be 52. So we'll add all this up. And I got minus 92. So this is equal to minus 92 divided by n minus 1, which is 5. So I'm going to have minus 18.4. So that's the covariance. I'm going to go ahead and get the correlation here. The correlation is equal to the covariance of x and y divided by the product of the two standard deviations. It's minus 18.4 divided by the product of 6.16 and 14.57. And that's about minus 0.205. So a slight negative correlation. So that takes us through parts A, B, and C. I wrote that down. I said it right. That's minus 0.205. Lost my, well, I don't know where it went next. Well, that's good. I don't know where that went. Maybe I can remember the spot. Okay, this is the part we already did too. Good. I'm going to get to move back and forth now. So anyway, we get down to, we've already got the correlation. So is there a linear relationship? We're going to write the hypotheses. HR is, there is a linear relationship between hours of training and worker productivity. And HO, and there's not a linear relationship between training and worker productivity, or between hours of training and worker productivity. Since we're looking at correlations, it might be beneficial to think of this HR as rho, the population correlation, not equal to 0. In other words, there is some non-zero correlation. And HO is that all we're observing is random error, that the population correlation could be 0. So this is a t-test, a two-tailed t-test. We're going to reject HO. If t-test is greater than some value or less than negative that value, and we had a sample size of 6. So the degrees of freedom is, I'll write that up here, degrees of freedom is n minus 2. We calculated 2 standard deviations, so that's 6 minus 2 is 4. It's a two-tailed test with O5. And so if you go to two-tailed test O5 and 4 degrees of freedom, you should see 2.776. So then we're going to compute the t-test, and that's equal to r, or r minus the hypothesized value of rho, which is going to be 0, divided by the standard error, which is 1 minus r squared. divided by n minus 2. So we had an R of minus 0.205, then minus 0, so I'm just going to leave that. The square root of 1 minus 0.205 squared divided by 4. What are you getting for that?
Negative 0.206.
Yeah, let's try this again. We're getting different numbers, and we're both getting different from what the calculator says. So minus 0.205 divided by, I think I know what I did. Second, square root. It opens one parenthesis. We need to open another one. Say 1 minus. And since it's squared, it doesn't make any difference if it minus 0.205 or 0.205 squared. Then close that parenthesis, divide by 4, and close that parenthesis. And you should get about minus 0.42. And that is what the calculator got. I got minus 0.41889. Yeah, the other way to get that 4.2 is just to do stat, test, then regression t-test. You'll come up with the right answer that way. And if you have it set up, then... Well, anyway, that is not greater than 2.776, and it's not less than minus 2.776. So you fail to reject HO. There may be no linear relationship. Well, I'm thinking of it. Sometimes I ask to forecast or predict using this for a given number of hours, predict what productivity is. So you could have get your A and B off of here and do that. But when you do make those predictions, make sure that the X's that you're using to predict from are within the range of X's that were in your original data. So in this case, the original data went from, on the X's, from 9 to 26. So for numbers between 9 and 26, you can just plug into the A equation, but it might not be that bad to go 1 or 2 on either side, but certainly you wouldn't want to predict Y for a value for a level of hours of training of 50. Another thing I might note in the context of this problem is, let's say we had rejected HO. Does that mean that there's a causal relationship, or that adding more hours of training will cause productivity to go up? And the answer to that is maybe. But there could be other variables that are affecting this relationship. It may be that people that have been there longer have had more hours of training and more productivity, and that may be what's causing both. So this is not necessarily a causal relationship. Okay, so on the next one here, if the p-value is 0.001 and the alpha or level of significance is 0.05, have you proven your research hypothesis is true? Okay. You will reject HO. That's true. But there's always a chance of error. So the answer is no. There's always a chance of error. You've supported that idea, but proven is a little bit too strong of a word for what you do with statistics. You can have strong support or strong evidence supporting that, but not proof. Why is it important to construct scatter plots when you examine linear correlations and regression? Well, a couple of things. One is you can have different sets of data that have the same intercept, slope, and correlation, but are nothing like one another. You may remember on maybe the second page of the Tufte text, he had maybe something that looked like that. These may not be exactly what he had, but something that looked like that. And even though those are vastly different data sets, well, that's not the best picture of all time, but they may have the same or similar slopes and that kind of thing. So you need to graph the data. It also might be that you have a non-significant relationship, but it might mask, even though it's not linear, it might mask some other recognizable relationship. So even though that's not a line, it's still worth recognizing that there is a relationship there. So draw the graphs. Central limit theorem, I'm not doing that again right now. You can go look at the last video. Okay, box plots. It says discuss the role of box plots as they relate to descriptive and inferential statistics, and maybe include some supporting graphs. So really there's two things that I think we've used box plots for over and over again. One is for the identification of outliers and extreme values. And remember that those affect the necessary sample size for quantitative analysis, like tests or confidence intervals for means or difference between means, for linear regression for that matter, and for ANOVA. But anyway, as far as just supporting graphs, if you had something like that, you need an N of at least 40. And if you had an extreme value, you need an N of at least 100. So that's one of the ways we've used it, is to identify outliers and extreme values, not just because of the N for quantitative. It may be that those are data that has been entered incorrectly. It may be that they're the most interesting items in the thing. If this was productivity, I might be more interested in that extreme value than anybody else in the place. I want to know why they're able to produce more. Okay, the other thing is really, we've used them to compare groups. So, for example, if we had something like that, that would just support the idea that there's a real difference between A and B. You can just see it visually. Whereas if something like that, you wouldn't suspect that there's a difference between A and B. Of course, if you on your projects, if you do a difference between means or an ANOVA, then I wouldn't expect you have a box plot that compares the 2 or 3 groups that you have in your data set. Okay, this next thing, well, hopefully by the time you see this, I'll send you an email that says, depending on which class you're in, Wednesday or Thursday, that you'll be reading chapters 4, 5, and 6 in the Tufte text. And basically, the changes he suggests are over here. But before we get to those, I'm going to talk another one that's, that he identifies, but that have been identified by other people as well. This is called the variable width notched box plot. The width, that means like the width that way or this way, designates the sample size for each group. So in this one, we had a much larger sample size in this group, really, than we had in any of the other groups. Then the notches. So when you've got this notch from here to here, that's a 95% confidence interval for the population mean. So that just gives you a little more information than the traditional box plot. And as you'll see when you read, Tufte thinks you should minimize the amount of ink and that it's easier to see what you have going on. So in this next one, where it's just lines, this really is just his redo of a box plot. So, and this is the same data as the variable width notch plot over here. So if we'll just look at this one on the far right, the width of this bar, that's also the median, but the width of that bar is the sample size, just like the width of the box plots were over there. And then this distance right here, or like on here, the darkly shaded thing, that's the 95% confidence interval for mu. And then the spaces here, right here, that's Q3, that's Q1. Of course, the line in the middle there was the median. And then there's your minimum value and your maximum value. Well, what he argues, and I agree with him, is there's just less to look at and just easier to visualize with this kind of layout than it is for the traditional layouts or for the notch box. And it provides a lot more information than the traditional box plot, because you get, in addition to the 5-number summary, you get information about the sample size for every group, and you also get, and I think this is a lot easier to read on his plot than the notch plot, you get the 95% confidence interval. By the way, I don't think we've talked about this in here, but in fact, I know we haven't. Interpreting confidence intervals. If you can see that two confidence intervals like this one and this one, that they do not overlap, then you know there's a real difference between, in this case, the medians, the population medians. But just because two things overlap, that doesn't necessarily mean that there isn't a difference. So there's another calculation you can do. I really haven't seen very many people do it, but I will tell you this, that in research about interpreting graphs, I've seen a study of medical doctors who misinterpreted that they thought if the intervals overlapped at all that they couldn't be a significant difference, there could not be a significant difference between means or whatever, but that's simply not true. I think I misspoke a minute ago when I said a significant difference between medians. It really does in this one and this one where there's no overlap suggest that there, or not suggest, it means that there is a difference between population means. But again, just because they overlap doesn't mean that they're not different. They obviously could be the same, but you have to go ahead and do the whole statistical analysis, in this case the ANOVA, since there are several groups, and the subsequent HSD or other approaches to identifying specific differences between means. Okay, this is another graph you'll see in Tufte, and to me, I haven't seen yet any software that will completely produce this graph, but I think it's about time. What this is every box on here is a scatter plot. So like right here and here, we have an X and a Y. So that's just the kind of scatter plot that we've been talking about already. But when we come down to this next one here, this has the same X, but a different Y. So now we can look at how X is related to different Y's. So here's another, this is the same X again. These could all be how much you spend on advertising, and you could have it could be maybe sales here, and any other kind of variables, and then there would be another y here. And so then also it's connected here. You've got the same y, sales again, and then another kind of x. Maybe in the first one here it was how much you spent on advertising, and maybe in this one it's the number of salespeople you've hired or the amount of money you've spent on market research or whatever. And so again, it's the same pattern over here. Same y as this one, same x as this one, now the same x as that, and another y. So what that allows you to do is go beyond a simple two-variable relationship to look at the interrelationships, in this case, among 1, 2, 3, 4, 5, 6 different variables. The other thing you'll see on here, and he'll talk about this in other contexts as well, there's different things you can do on here, is he's got these little, I can't think of what to go on. They're just what's called a rug plot anyway. But what this is each line on here corresponds to a particular value on the data set. So this point right here, you have a line here and a line up here. And that's true for every point on all of the graphs there. Another thing that you'll see sometimes is there's some software that will put histograms, not the greatest, on each axis. So you can see something about the shape of the data for all the variables that you have there. On this kind of thing, when they're connecting it up, these rug plots are certainly a more reasonable way to do it. But if you're just looking at one x and y, having the histograms or some other graphs there, you can even put box plots over there. That sort of brings me to another, I guess, point that goes beyond this test. Maybe I'll try and email you about this too. The last week or so, I've been looking at some different statistical software, and I'm using something called SysStat, which is very similar to SPSS. There's a couple of little differences here and there, but actually it does a lot more for a lower price than what you can do with SPSS. But even more, call this interesting or worthwhile to know, is there is a student version called MyStat. And you can go to www.sysstat.com and or just search for SysStat or MyStat. And anyway, look in there for the student version MyStat. It's a free download. You can keep it forever. And it does basically, in a little difference here and there, but it does everything that the $600 version of SPSS does. But it's free. That means it would be a great piece of software, statistical software, for you to have on your computer. Did I mention it's free? That's a good price. Okay, finally, and it's been a while since we've looked at one of these, but I think this is a pretty good thing to have on a test, maybe just about, well, any class. I think that one of the things people ought to get out of college is an ability to think critically. And this actually is the kind of passage that you might see on a GRE or a GMAT test for grad school that is designed to see a little bit about how you think critically. You would write essays about this, and it probably wouldn't be like a 20-word essay either. Well, anyway, we'll get a little bit of analysis on this. been some complaints about dizziness and nausea, and so they requested some cans returned for testing, and they concluded, so that's your conclusion, that the cans did not contain chemicals that posed a health risk. So I'm going to put this graphically and just say that, I don't know if I want to put no, but really no or limited health risk. That conclusion is based on the fact that chemists from Promo Foods tested samples of recalled cans and found that of 8 chemicals, most commonly blamed for causing these symptoms, 5 were not found in any of the cans. 5 of 8 not found. So based on that information, they conclude no health risk. They also say that there were the three of the other 8 chemicals are found in all canned foods. That's 3 of 8. And so that would be another thing. Though it's not their argument, I think it's worth noting that we did have those complaints. And, if we're evaluating this argument, I think we'd want to take that into consideration. Well, anyway, that's just a fairly simple argument that's presented here, and the point now is, or the next step then, I've just outlined at least the basic argument in the passage, or what kind of problems, or how would you critique this? And if you're doing this for one of these tests for grad school, don't put that there are no flaws in the argument. There will be. So anyway, a couple of things that you might want to know. First of all, just about the complaints themselves, I'd like to know how many of them were. I don't know if that's been 2 complaints or 10 complaints or 1 million complaints. Those would provide different amounts of information. On this 5 of 8 not found here, it does provide no information about sample size. I'm not sure if they tested 5 cans, 20 cans, or 1,000 cans, or if they took a random sample. I'm not sure if that's true. Or if they just selected the first 30 cans that came in. This may be something that's in some cans, but not others. Maybe not everybody has complained. I think also if they have, I don't know if they do or not, but if they have different plants, they might want to do what's called a stratified sample and make sure that they get a random sample of cans from each of the canning factors that they have. That's called stratified sampling. You don't have to name it, but you ought to recognize that we don't want to get everything from a limited number of the plants. Okay, on this 3 out of 8 that are in all of them, it doesn't say how much. How much of these chemicals are found in Promo Food cans? How much is found in the other canned foods? So what I'd like to know is there significantly more of any one or more of these chemicals in Promo Foods canned foods than there is in other canned foods? There may just be some tolerance level that has been exceeded by the cans for Promo Foods. Well, anyway, there's just a few ideas you could use in something like this. Of course, from here you want to go ahead and put this in some kind of sentence and paragraph form, because another thing that, at least if you're taking this for an entrance exam for grad school. So in addition to the critical thinking, they're looking to see something about your skills as a writer. Do you have your essay organized? Do you use effective transitions? Is the grammar correct? Are you clear? Do you vary your sentence structure? So they're going to look at a lot of things there in terms of writing, and then just the clarity and logic of your thinking. I believe that is, well, maybe not. That's pretty much it as far as we're going to go here. So hope you either will have, or have had a great holiday.